So we're going to start with a really, really simple question. Namely, we're going to start with the question of how does the spring move? So I happen to have a spring here. You can buy this for a relatively small amount of money. And you can imagine I take this spring and I just start it moving. And I were to walk along. And I can ask the question, well, what's happening to the bottom? So, the bottom of the spring, how is it moving? What can we say? It's moving up and down. Fantastic answer. I love that answer. Yes. Good. But can we be more precise?
It looks like a sine wave.
Ooh, it looks like a sine wave. Okay. Interesting. Yes? Sorry, what? It's oscillating. Sounds like something like harmonic motion. So let's start with the fact that it goes up and down. Now, we all agree on that. It goes up and down. But there's lots of ways to go up and down. And here's a couple of different potential candidates. Each one of these goes up and down. Maybe it goes up and then does an immediate, like, doo, in the other direction. Maybe it goes like some kind of a sine wave. Or maybe it goes up, sort of hesitates for a long time, and then whoosh, goes down, hesitates for a long time, whoosh. All of these go up and down. So which one's right? Now, I claim we can actually answer this question using some really basic ideas. But the way we get there is going to motivate why are we here? What are we doing? And what do we want to achieve? So we're going to go for this. We're going to answer it. And we're going to start with something called Hooke's law. Now, I actually don't have anything written down there. So there's a lot of space here for us to play with. Who knows Hooke's law? Okay. A lot of students yet to take physics here. Okay, who's willing to explain Hooke's law? All right, there's a person here near the front. Yes?
The energy of the spring's motion is related to the strength, like the spring constant, and then the distance that it was moved.
Okay, the energy, okay. I think there's another word for that. Force. Okay, so the force is equal to, there's a spring constant, okay, there's the constant, and the amount of it moved. So normally this is written down in the following way. Force equals suspicious gap, Kx. All right. Now, I can't help but notice there's a suspicious gap here. Okay, but before we talk about the suspicious gap, what is this saying? Now, if you take a spring here, and most springs have sort of a resting state. So this would be considered 0. The idea here is if you pull the spring, what does the spring want to do? It wants to go back up. And it says, no, don't do that. And the more you pull it, it says, no! It's going to have a stronger desire to go back up. So in other words, the force increases the further you pull it away from center. Now that is true for both directions. So in other words, pulling it down from 0 or pushing it up above 0. Why did I leave a suspicious gap there? Somewhere in the back. I was really excited about this. Okay, so what should I put there? A negative sign. Okay. Now, of course, purists would say, yeah, just assume K is a negative. Same result. But what is that saying? So here, if we're going down, so if X is negative, which way should the force be going? It should be pulling us up. So when X is negative, I want the force to be a positive amount. So that's the idea of that negative sign. Okay, so that's Hooke's law. And you're probably thinking, how do we go from Hooke's law to saying which one of these pictures is correct? Let's keep going with Hooke's law. What is force? Mass times acceleration. Okay, cool. So we can say mass times acceleration is minus k times x. What's acceleration?
Negative. That's gravity. The rate of change of the velocity?
Okay, rate of change of velocity. Yes, good. Someone was saying second derivative. Second derivative of what? Position, which we're calling x. Okay, cool. Interesting. So, if we're a spring, the mass times the second derivative of x is equal to minus k times x, where x is our position. Okay, so here, x equals position. Good stuff. All right, now we're going to do a little bit of magic called divide by m. And the way it works is you divide by m. Okay, so we're moving that across. All right, so the second derivative is essentially the negative of some constant times x. Now, let's just make a simplifying assumption. Let's assume this equals 1. Now, it doesn't have to equal 1, but it's our first day. Let's be kind to ourselves. We like ourselves. So we're going to make that simplifying assumption. All right. So we've come to the conclusion, starting from Hooke's law. And Hooke's law, it makes sense, right? That force should be like the more you pull it, the stronger it should be trying to get back to where it started from. That's what Hooke's law says. It's very intuitive. So we've come to the conclusion that x double prime, the second derivative of x, is minus x, where x is position. And now we say, okay, great. So we started with, here's this physical thing, here's this reasonable relationship, and we'll call it a law. I said, all right, now let's follow the consequences. And we ended up with this equation that involves derivatives. By the way, differentials is really just another pseudonym for derivatives. So when we talk about differential equations, it's an equation that involves derivatives. So now, this is our bread and butter for this semester. Working with some equation that involves derivatives. And our goal is to understand, what is x? So now, we start reaching into our databases and say, do we know any function such that when we take a derivative twice, we get back the negative of what we started with? Yes, we saw the sign. And it opened up our eyes. We saw the sign. Now, I'll put sine of t. It's not sine of x. X is position. So there's some other variable involved. Is that the only one?
Cosine.
Okay, cosine. They're like cousins. They go together. Cosine. Are there any others?
Lots.
Lots? Okay, so if there's lots of them, give me another one.
Secant.
Secant, if you take the derivative of secant twice, you'll get secant squared, tangent plus other stuff.
E to the negative x.
If you take the derivative of e to the negative x once, you'll get negative e to the negative x, right? But then if you take it a second time, the two negatives combine, yes?
Any sine or cosine with a coefficient.
Whoa, well, that's very profound. Okay. So, let me repeat that. Any sine or cosine with a coefficient, which means you could scale it. So, in other words, not just like sine, I could do like twice of sine. Or I could do like -5 of sine. Or so forth and so on. So, something like a times sine of t. Or b times cosine of t is an example. Can we do anything else?
I don't want to, but we could do e to the ix.
Why don't you want to?
Because then we have to deal with imaginary numbers.
It does sound complex, doesn't it?
Yeah.
If we do that. I told you the jokes are not great, but come on. At least you get them. In fact, it's not bad to imagine that. But there's something about I think there may have been some hands in the back. No? Yes? Whoa, we can add them. Oh, this is so good. You know, you might think I planted somebody in the audience and like said, okay, I'll pay you $5 if you give me the right answers. No. This is, you can add them together. A sine plus B cosine. And, okay, you can check. It's easy. You know, in some sense, it's easy to check an answer, but it's hard to get an answer. All right. Is there anything else? What about 0? Is 0 valid? Yeah, in fact, that's the spring that's very boring in that it's not moving up and down. It's just staying where it is. It's a valid answer. Does that show up in our solutions?
Yeah. A and B is 0.
If A and B are 0. I'm sorry, can we have negative 0? Yes, negative 0 also works. You choose negative 0 for both. How about something like sine of x plus 2? That, I claim, is a solution. Does that also show up here? Ooh, have I stumped you? Where's my trig class people? They're like, yeah, I love trig.
Yes, probably.
Yes, it actually does show up there if you use various trig identities. It turns out that this expression here can also be written as, and of course we all love this fact, square root of a squared plus b squared times sine of t plus some fixed constant. You don't need to know that. But the point here, and the great aha, says that's it. This is the answer. So it is the case that springs do behave like a sine curve. It's not a coincidence. Every single spring that you will ever see, assuming that it's one that can satisfy Hooke's law will force it to behave like a sine curve, which is good. Now you might say, do I really need to know it's a sine curve? Well, maybe. You can imagine I have a spring moving, and I'd like to be able to say I know exactly where it is at any given time, because I don't want it to collide with something else. It's good to know these things. So this is sort of like the spirit of where we're going. It's like, okay, we start with a motivating system example. We figure out a nice equation. We have a differential equation. We try to say, okay, what function satisfies that differential equation? Now, you probably think, wow, this was easy. Is it always going to be this easy? No. You can imagine that I change things ever so slightly. So we now know, for example, if I have this one, x double prime plus x equals 0, it's like, okay, that says I move up and down. What if we had x double prime plus 0.000001 x prime plus x equals 0. So in other words, somehow velocity was coming into play for some reason. Or maybe we had x double prime minus 0.00001 x prime plus x equals 0. They're so close to this. Does it matter? Does it make a difference? Can we tell? Because now we can't guess. Not very easily. And I will tell you, it does make a difference. One of these two, they both look like springs. And you can't really tell the difference for a long time. But one of them will eventually peter out. So in other words, you have your spring, and it'll start to more or less go down. The other one is going to oscillate and get really, really big. And usually that leads to some catastrophic thing. Can you tell which is which? You will. You will. It's coming. You'll get there. All right. So lots of good stuff to look forward to. Okay, so now I'm getting to restate a lot what we just talked about. So what's a differential equation? It's an equation which involves a derivative. It can involve multiple derivatives. It can involve derivatives of higher order. But that's what it is. And here are some examples. There's lots of different ways to write it. And we're going to learn a little bit about the taxonomy of differential equations. There's lots of different ways that we might have, there's various assumptions of the form it takes. Now, sometimes you'll see a derivative written as dx dt. So here this says there's some function of x, which is a function of t. And when you take its derivative, it's the original function cubed plus x times t. Now, that's a perfectly fine differential equation. Here's one that involves the second derivative. The second derivative of y with respect to x minus 5 times the first derivative of y with respect to x plus 6 times the original function of y equals 0. On this next line, y double prime minus 5y prime plus 6y equals 0. What do you notice about these two equations? Yeah, they're the same. It's just a notational thing. Now, you might say, really, Steve? Really? Are they the same? Well, the one small subtlety is that in the second one, we don't know the name of the other variable. So usually we think of y as a function of something. I'm not saying what it's a function of. But there's a lot of consensus that when you see derivatives involving y, we say, oh, we'll call the variable x if we don't see it there. So you might see something like x dy plus y squared dx equals sine of x dx. So when you see just like the dy's and dx's separated like this, we usually refer to these as differentials. And again, it's just another way of writing things involving derivatives in a peculiar way. And of course, you can get complicated. You can get something really exotic. This y prime plus arc tangent of y prime equals 1 over x squared plus 1. It is a differential equation because it involves y prime. It's pretty hopeless. But, you know, if you've taken Calc 2, you already come in knowing things are going to be pretty hopeless. So that shouldn't surprise you. But that's all right. Now, there's this question, why do we care? Why should we study these things, differential equations? And hopefully the spring gives us a nice demonstration where we can say, hey, you know, it's oftentimes easier for us to describe how things change, and then we can start with that to figure out how things behave. So we start with an understanding of changes and then build up to saying, well, what's the actual function? So there's things that we want to do. So this comes to our goal. It's like, okay, how do we look at the differential equation? How was it set up? All right, well, that's usually not too bad. There's a lot of intuition. We say, okay, what's our intuition? And you get a lot of this in physics. We're not going to do much of this. We'll do some. And then I will say for much of the semester, we're not going to worry too much about that. We're just going to be saying, hey, here's this equation. It came out of a black box. Don't worry what it means. Just solve it. And what does that mean? Well, find the function. What is the function? Okay. You'll notice we say ideal. It's hard to do in general. It's super easy to write down a differential equation you can't solve. In fact, I would say it's much easier to write down something you can't solve than it is to write down something you can solve. You might leave this class thinking, every differential equation can be solved. No, not even close. Hopeless. But we'll show you lots of cases that can be, and they're important cases. But even if we can't solve it, we can still do other things. We can say, well, what's the understanding of how it behaves? What happens in the long run? Or maybe we can say, well, look, what's happening approximately in the short run? We can answer those types of questions, and that's not too bad. Now, we have worked with one very special type of differential equation in calculus, namely y prime equals f of x. Now, is this a differential equation? Yeah, there's a derivative. So it is a differential equation. How do you solve it? Yeah, antiderivative or integrate, if you like a smaller word. So we can solve those. So let's just solve one. So find y. So here we are. We have this differential equation. Y prime is e to the 2x plus 6 cosine 3x. Find y. All right, so what is y? Well, take the antiderivative. Antiderivative of e to the 2x? Half e to the 2x or 2 e to the 2x? Yeah, it's a half. Yeah. You're right. But I said that, Steve. I know. I just like to test. Antiderivative of 6 cosine 3x? 2 sine 3x or negative 2 sine 3x? It's positive 2. Now it's like, oh, Steve, you're messing with it. It's been a while. Yeah. And so, cosine is that weird thing, cosine sine, where you have to keep track integration versus differentiation. Now, is this an answer for y? But what's my question? Is this unanswered? Yes, it is an answer. Is it all of them? No. Where do we get all of them from? Plus c. Yes. Now, you'll notice that when we take an antiderivative, we have to add on a constant. We need a little bit more. Now, this makes sense, because every time we take a derivative, we kind of lose some information. So when we're working our way back, we should throw in somewhere there should be a constant involved. Now, you might say, okay, going back to our Hooke's law example, because this has 2 derivatives, so how many constants should we see? We should see 2, right? And we do. Boom, boom. But notice, they're not plus a. They're showing up in other places. Ooh, interesting. Wow, this is good. This is going to be a good class.